We're going to start our work with transcendental functions by doing a really quick review of the properties of the natural logarithm. We went over this back in August when we were doing our pre-cal review. So we know these already. I just want to make sure that you put them in your notes again, or that you review them in your notes if you've already got them there. And then we're going to start talking about, not only in this lesson, the natural logarithmic function, but we're going to have to bring the natural exponential function into this discussion as well. And so there's liable to be quite a few videos with this lesson, but it will shorten up some of the lessons later on. So here we are, the properties of the natural logarithm. Again, we know all these, they're already in your notes, but we're going to review them again. If a and b are positive numbers, a and b are positive numbers, and r is any rational number, then we can count on these four properties of the natural logarithm. We can count on the fact that the natural log of 1 is 0, and here's why. Because the natural log is log based e, and the log based e of 1 equals 0, because when I use the equivalent exponential form of this logarithm, it states that e to the 0 is 1, and that's always a true statement. So we can count on the fact that anytime we see the natural log of 1, we can replace it with 0. So we're going to use that a lot in our work with the natural logarithm. These three properties are what are already in your notes. Remember, the natural log, or the logarithm period, but we work with the natural log mainly, of a product can be written, or is equivalent, or can be substituted by the natural log of the first factor plus the natural log of the second factor, no matter what the factors look like. So the natural log of a product becomes the sum of the separate natural logs. The same here for a quotient. The natural log of a quotient of a over b is the natural log of the numerator expression minus the natural log of the denominator expression. And this one is really handy. This third one we're going to use a lot. This one says that the natural log of some expression raised to a power, no matter what that power is, it can even be a rational expression, that the natural log has a property where you can turn this expression into a product. You can pop the power down front, and it's the power times the natural log of a. So those are three properties that you are going to be, actually the four properties, but these you already know, and we're going to use these a lot when we start working with the natural log function. So make sure they're in your notes. Make sure that you understand the relationships. So let's talk about the natural logarithm. Let's talk about logarithms in general. What are they? Why do we need the log functions? Well, as a quick reminder, in pre-calculus, we learned that one-to-one functions are the functions that will have inverses. One-to-one means that they pass that horizontal line test. Remember that? So that when we reflect the graph over the line y equals x, the result will still be a function. So one-to-one functions will have inverses, and inverse functions, the domain and range of one function map to or become the range and domain of the inverse function. And we'll see that when we talk about natural exponentials and natural logarithms. We also learned in pre-calculus that exponential functions of the form a to the x are one-to-one functions. Finding their inverses was impossible without logarithms. This is what gave birth to the logarithmic functions, because we did have these exponential functions, but when we talked about their inverses, or functions that would undo them, we hit a problem, because none of the other functions, polynomials, rationals, all the other elementary algebraic functions, would not undo the operation that the exponential functions were doing. So that gave birth to logarithmic functions as inverses of exponentials. That's why it's going to be impossible for me to talk about the natural logarithmic function without talking about the natural exponential function e to the x as well. So remember, if we are given a function f of x equals a to the x, just a general transcendental exponential function, also known as y equals a to the x, the inverse is the logarithm. So if we're given y equals a to the x, and I prefer to write it like this, f of x equals a to the x, and we could be given that, we'll call it g of x equals the log-based a of x. We know that inverses have this quality, inverse functions, since the domains and ranges are swapped, that when we compose inverse functions in either direction, f of g of x or g of f of x, if you'll recall, we should just get what we started with back as the result. So f of g of x is going to look like the function a to the x feeding it the function g of x. So that is a to the log-based a of x. These two functions undo each other, and sure enough, we get mapped right back to that original domain function. And it should work in both directions. If we take log-based a and we feed it not x, but we feed it the function a to the x, these two functions, operations, undo each other, and we get mapped right back to the domain value where we started. So these functions are inverses of one another. All right? There are inverse exponential functions and logarithmic functions, and then there is the equivalent, which we'll see here in a minute, the equivalent form of the logarithmic function. So remember, a is the base of the exponential function, and it's also the base of the logarithmic function. X is called the argument or antilog. It is the expression that is fed into the logarithmic operation. And y is the result of that. Y is the actual logarithm. The result that we get from picking an x value or putting in an expression in x and then picking an x value and taking the log-based a of that value gives us a real number value, which is y. So remember, the logarithm is the inverse function of the exponential function and vice versa. All right, we're also going to need, in this context, when we talk about the natural logarithmic function, we're going to need to know the change of base formula for logarithms. This is also in your notes from a prior lesson way back in August when we did our pre-cal work. If we have the log-based a of the expression x, we can change the base to any base we like. Here I'm calling the base b. But we can change the base a to any base that we like by taking the log of the new base of x over the log of the new base of a. We like to use the base of e in calculus. So what the change of base formula for us is going to look like, and what ought to go in your notes, is that log-based a of x for us is going to wind up looking like the natural log of x over the natural log of a. Remember, natural log is just an equivalent way of writing log-based e. All right, now, if you get confused over which goes in the numerator and which goes in the denominator, this is how I remind myself. It's kind of silly, but it always works. When you write the log to the base is always below the antilog or the expression. So since this is above this, that reminds me that this goes in the numerator and this goes in the denominator. Now, since a is some positive real number, and it will be when it's plugged into the natural log function, understand that 1 over the natural log of a is a coefficient to the function natural log of x. This is a real number. This is some real number. If you have a as a real number and you got your calculator and you hit the natural log of any real number, as long as a is not 0 and as long as a is positive, you're going to get a value. This is the exact value. Once you pick up your calculator, you're going to get a decimal approximation. Remember all that. And here's the actual function. So the natural log of a, 1 over the natural log of a, is the coefficient. All right, so we can just pop those coefficients, pop our constants out front. And when it comes time to do calculus, there's the meat of the function that we're going to do the calculus on. So just for future reference, you'll see that examples that we do. All right, so the logarithm with base e is called the natural logarithm. Here is its own special notation. Please do not call it ln of x. It is not ln. I've had students in the past call it line of x. I'm not really sure why. I want you to call it, every time you see it, the natural logarithm. It's the natural log of x. It is log based e of x, or the natural log of x. And that's what I want it referred to as. All right, so remember I told you not only do we have functions that are inverses of each other. Here are two functions that are inverses of each other. We saw this when we did our pre-calculus work. But every logarithm has an equivalent exponential form. This is not, put this really big in your notes, this is not the inverse function. This is completely not the inverse function. This is an equivalent form of the logarithm. When I put an x value in here and take the natural log of it and I get a corresponding y value, it's going to be the same y value here that if I put that y value into e, it's going to give me that x value. All right, so this x and y points, the x and y points on the graph of this function are identical to the x and y points on the graph of this function. These functions are two completely unique functions in the plane that don't have anything to do with one another other than their inverses. So don't get the equivalent form for a logarithm or natural log confused with the inverse function for the natural log. So I want to make sure that's clear in your notes. All right, so the inverse function for the natural log of x is e to the x. When you are working with e to the x and you want to kind of understand what's going on, remember that e lies on the real number line between the integer value of 2 and the integer value of 3. As a matter of fact, it lies a lot closer to 3 than it does to 2. So anytime that you are using e, if it's confusing you or it's tripping you up, just to help yourself, just for a little while, but I want you to get over this quickly, you can replace e with 3, because however 3 behaves is pretty much how e is going to behave, because it's a value very close to 3. For some reason, kind of like when you're first introduced to pi, a lot of students have trouble working with e. Remember, e is just a real number. Like pi is a real number, e is a real number, and it's an exact real number. All right, but if you get confused right at first and you know all the e's confuse you, you can go off to the side just for your benefit and see how 3 would behave in the function that you're working with, and that's how e would behave as well. All right, so let's look at the graph really quickly of e to the x. So in order to develop the derivative rule for the natural log function, first, we're going to develop the rule for the natural exponential function. And you'll see why, because we can use an implicit differentiation to get to the derivative of the natural log function. So let's look at the graph of y equals e to the x just really quickly. We've already seen it. We know some things about it. In our calculus work, the graph of the natural exponential function has some really great properties. Now just remember, in general, it only has one intercept. That's a y-intercept. So it always goes through the point 0, 1, the parent function does. It will never equal 0. E to the x will never equal 0. Why will it never equal 0? Because the horizontal line, y equals 0, is a horizontal asymptote to this function. E to the x, the parent function, never crosses or touches the horizontal axis. All right, I'm going to stop there, and we're going to come back and we're going to talk about this tangent line through the y-intercept point. So look for the next video.